In the least mean square algorithm, we first will learn the steepest descent method. That's the first approach. For this approach, the cost function is the instantaneous error energy. As we know, the system will be updated with any individual input training sample. So here, if we have n training samples, so the synaptic weight will be updated n times. The theory behind the steepest descent method is the Taylor series expansion. Here is the Taylor series expansion. In Taylor series, for a function value at x, that equal to the summation of infinity derivatives of f evaluated at point A. So here, this one is the first order term, second order term, third order terms until infinity order terms. Here, if we only using the first two terms, that is called the first order Taylor series. In the steepest descent method, the cost function is updated using the first order Taylor series. Here, the cost function epsilon wn plus 1, that's equal to the cost function from previous training sample wn, and then plus the gradient of cost function multiplied with the difference of the w between n plus 1 and n. Here we got the updated cost function, that is epsilon wn plus 1 and equal to the cost function from previous sample plus the transpose of Gn multiplied with delta Wn. So let's look at each terms. First, the delta Wn is the difference between the weight from n plus 1 samples and the weight from n sample. And the Gn is the gradient of the cost function. Here we're using this upside down triangle, we call it nabla. So that is nabla epsilon Wn. So far, we learned the related theory about the steepest descent method. Now let's figure out how to apply this into a synaptic weight update. Let's start from the cost function. We know that is the instantaneous error energy. Following previous slides, we need to find the gradient of the cost function respect to w. In case you already forget what is the gradient, I bring this definition here. That is the gradient definition. That is the partial derivatives respect to w0, w1 until wn. Let's back to this slide. Here we know this is the gradient. So here we can tell that's equal to this guy. So this one equal to nothing, but equal to 1 over 2 and dw and e square. If you do this part, and you will get 2 multiplied with dE dw, and 2 multiplied with 2, you will get cancel this 2. Now you figure out why we need to add in 1 over 2 in front of e square. So the gradient of w equal to this guy. So here we know E actually equal to nothing, but equal to D minus Y. And if we plug E equal to D minus 1 into this equation, that is something we're going to get. So that's the nabla epsilon W equal to D minus Y multiplied with partial derivatives of D minus Y respect to W. Since we know the Y is nothing but equal to the transpose of X multiplied with W. So if we plug this one, we replace Y as this equation, we will get this is the gradient of the epsilon W. So here we know D is a constant. That means if we get in the D over dW, that equal to 0. And we know the partial derivative of xt W and over W, that is nothing equal to X transpose. So then if we put them together, we will get in the final gradient for the cost function, that equal to Y minus D multiplied with X transpose.